I would like to start by thanking the organizers for their kind invitation. I will talk about truncated Toeplitz operators, and some particular forms of these truncated Toeplitz operators have been studied for many years under different forms. But it was this paper by Saracen in 2007 that stimulated the current interest in the topic. As you can see, for instance, if you, by these two recent surveys, one of them really very recent. They appear in connection with many topics in mathematics, physics, engineering. They are complex symmetric operators. In fact, they have a very deep connection with complex symmetric operators, which I will not be talking about. They are connected to finite time or finite interval convolution equations, which I will try to show, and etc. And in this book, it is mentioned that while some very natural operator theoretic questions regarding truncated Toeplitz operators, such as when they are normal, self-adjoint, unitary, and so on, are beginning to be answered. Others, such as a description of the spectrum, are almost completely open. And this is exactly the main purpose of my talk, to present results leading to a clear description of the spectrum of truncated Toeplitz, of a significant class of truncated Toeplitz operators. They have been studied mainly in the context of the unit circle and the unit disk. This is what appears in almost all the literature. But since I will be motivated by applications where the natural variables are time and frequency, I will work in the setting of the real line and the Hardy spaces of the upper and lower half planes. And I will be talking also about asymmetric truncated Toeplitz operators, which are a natural generalization of both truncated Toeplitz operators and rectangular Toeplitz matrices. My talk will be of a general nature. I will skip all unnecessary computational details, and all the results can be found in these two recent papers, joint papers with Jonathan Partington, one from 2016 in Journal of Mathematical Analysis and Applications, and then the other one has just appeared in Journal of Operator Theory. Now, I will start by some notation, starting by spaces, and then afterwards operators. So I will denote simply by L2 the space of all square integrable functions on the real line, and I will define the Fourier transform, which is an isometric isomorphism in L2 of R, in this way using this integral. Now, if I have any function in L2 of R, of course we can decompose it uniquely as a sum of a function supported in R plus and a function supported in R minus. And if we take this definition of Fourier transform, because you also find it with a minus here, but I prefer this one, because if we use this definition of the Fourier transform, then the Fourier transforms of functions in L2 of R plus are functions which are analytic in the upper half plane, and functions supported in R minus have a Fourier transform which is analytic in the lower half plane. And these spaces, the Fourier transforms of L2 of R plus or R minus, are the Hardy spaces of the upper and lower half planes, which I denote by H2 plus and minus. So here H2 is not a Sobolev space. I denote by H2 plus and minus the Fourier transforms of these subspaces of L2 of R. So L2 can be decomposed as a direct sum of L2 of R plus L2 of R minus. And if I apply the Fourier transform, this induces another decomposition, another orthogonal decomposition in L2, which is H2 minus plus H2 plus, where now H2 minus and H2 plus are supported on the whole real line, but they have analytic extensions to the upper or lower half planes. And I denote by P minus and P plus the projections associated to this direct sum decomposition. Now, if we consider L2 of R plus, this in its turn can also be decomposed as a sum of functions, a space of functions supported in 0, 1, and functions supported in 1 plus infinity. So we have this direct sum decomposition of L2 of R plus, and I can apply the Fourier transform similarly. So L2 of R plus will give H2 plus, and this, which is just a translation by one to the right of the space L2 of R plus, will be by the Fourier transform transformed into H2 plus times an exponential which corresponds to the translation. And what is left, meaning the orthogonal complement of this, is what we call the model space associated to this function e to ix. And I denote by p of e to ix the corresponding projection parallel to this space, so from H2 plus onto k of e to ix. Now, this function e to ix, sorry, I made a mistake. This function has the following properties. It is analytic and bounded in the upper half plane, and it has modulus 1 on R. So it's called an inner function. And my talk will depend a lot on the properties of inner functions. Of course, if I have a between 0 and 1, the same will happen with this exponential, and the same will happen with the quotient of this exponential by this exponential. So we say that this is an inner function because it has the same properties, and it divides e to ix. So it also has a model space associated, just as in this case, and this model space consists of the Fourier transforms of functions supported in 0a. This model space, of course, is contained in that model space, and this, in fact, is equivalent to saying that this inner function divides this inner function. Now, these are inner functions which have no zeros in the upper half plane. But they are called singular inner functions, but there are simpler inner functions. The simplest inner function, of course, is 1, but we can have also a very simple inner function, x minus I over x plus I, and its powers, its non-negative integer powers. And of course, we say that all of them are inner functions because they are analytic and bounded in the upper half plane with modulus 1 on R, and 1 divides R squared, and so on until R to the power n. And we can do the same. We take H2 plus, consider H2 plus multiplied by this inner function, and then take the orthogonal complement. And the orthogonal complement will be the model space associated to this inner function with the projection P of Rn, which consists of the Fourier transforms of finite dimensional linear space, which consists of decreasing exponentials supported on the right half line. And in general, we can define for any inner function, which means a function which is analytic and bounded in C+, with modulus 1 almost everywhere on the real line, we can define analogously the model space as the orthogonal complement of theta multiplied by H2 plus, and I will denote by p theta the corresponding projection. This model space is finite dimensional if and only if theta is rational, which means that it will be the product of factors, each of which has a 0 in the upper half plane and a pole at its conjugate, which is in the lower half plane. So it is rational and, of course, analytic in C+, with modulus 1 on the real line, like any inner function. In this case, k theta has exactly dimension n, which is the number of zeros of the finite Blaschke product. Now, about operators, let me consider convolution operators on L2 of R+, which associate to each function in L2 of R+, a function which is, assuming that to begin with that gamma is in L1 of R, associates its convolution with gamma multiplied by the characteristic function of R+. And since the Fourier transform of L2 of R+ is H2+, and this projection is P+, which corresponds via the Fourier transform to multiplication by the characteristic function K+, then if the Fourier transform of this gamma is G. We know that the Fourier transform of the convolution is the product of the two Fourier transforms. So, using the Fourier transform as a kind of dictionary, we are led to this operator, which is unitarily equivalent to that convolution operator, which is the Toeplitz operator with symbol G. It's an operator from H2 plus into H2 plus that associates to each F plus the projection of its multiplication by G. We don't need gamma to be in L1. We can do this for any G belonging to L infinity, essentially bounded. And so the Toeplitz operator with symbol G is just the compression of the multiplication operator to H2 plus. Now, if I had started not from an operator associated to a single convolution equation, but to a system of convolution equations with n unknowns, then I would be led similarly, exactly in the same way, I would be led to a Toeplitz operator, now with a matrix symbol, which is defined precisely in the same way. The only difference is that now this is a matrix function and this is a vectorial function, and which is the compression of multiplication by this matrix function to that space. Although the definition is entirely similar, what happens is that Toeplitz operators with matrix symbols are much, much more complicated to study than Toeplitz operators with scalar symbols. And this will be important for what I'm going to say next. Now I can consider also, instead of convolution operators on L2 of R+, I can consider finite interval convolution equations in 0, 1, for instance, in L2 of 0, 1. And so I have here similarly, okay. So I have here similarly the convolution of f with gamma, now multiplied by the characteristic function of 0, 1, and the Fourier transform of the space L2 of 0, 1, now, as I said before, is the model space associated to this inner function with a projection that, via the Fourier transform, corresponds to multiplication by the characteristic function of 0, 1. So we can use analogously the Fourier transform as a dictionary, and we have these operators A, G, I, e to ix from this model space into this model space, which corresponds to this by the Fourier transform, associating to each f in this model space its multiplication by G projected into the model space. And so for any G belonging to L infinity and any inner function theta, I define the truncated Toeplitz operator as the compression of the multiplication by G to the model space instead of H2 plus. But since we can write P theta, P plus instead of P theta, it's exactly the same, we can also think of this as the compression of a Toeplitz operator to a model space K theta. Now, it is to think about these operators, it has always been very useful to me to think of them in terms of some models, and the best models are those that we are better used to. So for me, it's useful to think of this as a system where you have an input and an output, and which is characterized by some transfer function. So you have the input, consider only the right half of the input, then you take the output and truncate it to the right half. This is what corresponds to a Toeplitz operator, from my point of view. But if you truncate the input to 0, 1, and then take the output and truncate it again to 0, 1, then this is what corresponds to a truncated Toeplitz operator. You can think of it in terms of other things. For instance, a very well-known operator, which is of this type, is the Volterra operator. Because the Volterra operator, which is defined like this, is simply the convolution of a function in L2 of 0, 1 with a rectangular impulse multiplied by the characteristic function of 0, 1. So the Volterra operator, via the Fourier transform, is in a very simple way unitarily equivalent to a truncated Toeplitz operator, where now we have this symbol, which is the Fourier transform of this rectangular impulse. And it's a very nice symbol because it's analytic in the upper half plane. In fact, it's entire, but it is bounded only in the upper half plane. And it is continuous on the whole real line because there's no problem with this zero because we have another zero in the upper half plane. So this is a very well-known operator, which is unitary equivalent in a very easy way to a truncated Toeplitz operator. If we want to think of operators in infinite dimensional spaces, for me, this is the best model. But we can also think, because other people are used to other things, we can also think of the finite dimensional setting. And in the finite dimensional setting, for instance, for this model space, which I considered previously, truncated Toeplitz operators are just finite Toeplitz matrices characterized by the fact that they have constant diagonals. Now, whether you think in terms of a model which is a convolution operator or a system or a matrix like this, which can be considered as a truncation of an infinite Toeplitz matrix representing a Toeplitz operator, if you think, you see that there is no reason why we should truncate the input and the output in the same form. In fact, in signal processing, for instance, you almost never truncate the input and the output in the same form. Just think of what we do when we take a photocopying machine and we reduce the image. Of course, we don't truncate the input and the output in the same form. And also we can think of rectangular Toeplitz matrices, which naturally appear in many applications. And it's clear that we don't have to truncate an infinite Toeplitz matrix as a square matrix. We can truncate the rows and the columns in a different way. So it makes sense to define asymmetric truncated Toeplitz operators, taking two eventually different model spaces to eventually different projections. And we have the asymmetric truncated Toeplitz operator from k theta to k alpha with symbol G, defined analogously, but now with two different projections involving two different model spaces. Of course, when alpha is equal to theta, there's a small mistake there. When alpha is equal to theta, we just have the usual truncated Toeplitz operators. Now, all these operators have something in common, which is they are highly non-self-adjoint. But they have also great differences, for instance, as regards their relation with their symbol. And this is connected with the following question. Which symbols give the zero operator? When is the operator equal to zero? And if we have a Toeplitz operator, the answer is very simple. The operator is zero if and only if the symbol is zero in L infinity. So this means that that the symbol is unique, essentially unique. If two operators are equal, they necessarily have the same symbol, and that's it. But for truncated Toeplitz operators and asymmetric truncated Toeplitz operators, this is not the case. This was proved by Saracen in this paper in 2007. For truncated Toeplitz operators and for asymmetric truncated Toeplitz operators in this paper that I mentioned before. And the answer is like this. The operator is zero if and only if the symbol consists of two terms. One, which is a function analytic in the upper half plane, and which I will call to the right of alpha. And another one here, which is analytic in the lower half plane, and which is to the left of theta bar. And this means this has many consequences. I will mention just a few. One is the following. If we have any symbol in L infinity, it can always be decomposed into four terms. One term is of this type. The other term is of this type. This corresponds to the zero operator, so they don't count. And what is left can be decomposed into two. This is not a unique decomposition, but by some normalization it becomes unique. So what's left consists of two parts. One which is analytic in the upper half plane and belongs to this modified model space. And this, whose conjugate is analytic also in the upper half plane. So this is analytic in the lower half plane and belongs to this also modified model space. So what this means is that while the Toeplitz operator sees the whole symbol, so the symbol determines the operator, but truncated Toeplitz operators and asymmetric truncated Toeplitz operators don't see the whole symbol. They just see this part of the symbol. So you can have very different symbols, even things which are unbounded here, it doesn't matter, because the operator does not see what happens there. And another consequence which comes directly from this is the following. If theta, and I will always suppose that alpha divides theta, otherwise things can become very complicated. So if theta is a finite Blaschke product, so in the finite dimensional setting, all elements in the model spaces are rational functions. So this means that I always have a rational symbol. I can replace any symbol, however complicated, by a rational function which is of the same degree of simplicity as the model space that we are considering. And this is very important to simplify things. Now, this difference, this enormous difference between Toeplitz operators and truncated Toeplitz operators and asymmetric truncated Toeplitz operators can be seen in terms of this notion of equivalence after extension. This was presented by Bart and Tekhanovsky in '92, and it's as follows. We say that two operators between Banach spaces are equivalent if we can relate them on the left and on the right by some invertible operators E and F. They are equivalent after extension if we can extend them by some identity operator in such a way that the extended operators are equivalent. So we have this E and this F now on the left and on the right of the extensions. And operators which are equivalent after extension share many properties. For instance, I will use this notation to say that T is equivalent after extension to S. For instance, their kernels are isomorphic. The image of one is closed if and only if the image of the other. The codimension of the image will be they will be isomorphic, these two spaces. So if the image is finite dimensional, these two are isomorphic. One is invertible if and only if the other is invertible. One is Fredholm if and only if the other is Fredholm. And the Fredholm indices will be the same. So many properties from one can be deduced from the corresponding properties from the other. They do not share the same spectrum, but I will show that this doesn't matter. And it turns out that, as we proved in this second paper, asymmetric truncated Toeplitz operators, and therefore also truncated Toeplitz operators, are equivalent after extension to Toeplitz operators, but now not a Toeplitz operator with the same symbol, a Toeplitz operator with a matrix symbol, where this G, which is the symbol of the truncated Toeplitz operator, appears only in this non-diagonal entry. So if we look at it from this point of view, you see immediately that contrary to the Toeplitz operator with symbol G, now the new Toeplitz operator, which has a matrix symbol, of course it cannot be determined uniquely by G, because you will need some information, some additional information in theta and alpha. And in this matrix symbol, the two informations are separated. You have the information on the model spaces in the diagonal, and the information on the symbol here, in this non-diagonal element. No, as I said, I will skip all computational details. They would not interest you at all. But we also do have the explicitly the invertible operators E and F on the left and on the right, so we can make the correspondence between one and the other completely, in a completely explicit way. And we can study the kernels, the Fredholm properties, invertibility of asymmetric or symmetric truncated Toeplitz operators from the corresponding properties of Toeplitz operators with matrix symbols of a particular triangular form. Now, what about the spectrum? Because they don't share the same spectrum. But this doesn't matter for these operators, because when we want to study the spectra, we study this operator in the model space. But this operator in the model space is just another truncated Toeplitz operator where we modify the symbol. So it is equivalent after extension to a Toeplitz operator where we just modify this non-diagonal element. I'm not interested in the spectrum of this operator, which would be rather difficult. I'm interested in another Toeplitz operator of exactly the same kind, with just a slightly different non-diagonal element. So we just have to study operators of this type. And this is well known. This appears in any good book on this. Maybe not exactly in this form, but it is there, that a Toeplitz operator with matrix symbol is invertible if and only if the symbol admits a factorization of a certain kind, where one factor is analytic in the low half plane, the other factor is analytic in the upper half plane, with an additional condition here, which is that this must be bounded, because this is precisely the inverse of this operator. So it is invertible if and only if this factorization exists, and one of the conditions is that this is bounded, and if this is so, it will always be bounded, for instance, if G minus and G plus are bounded in the corresponding half planes. Sorry, I made some mistake. This is very bad for me. Sorry. So we have in particular, using the equivalence after extension, I would just like to say the following, that whether this factorization, in the matrix case, in the scalar case it's much easier, but in the matrix case, whether this factorization exists and how to obtain the factors explicitly, this is another question, and a very difficult one. But fortunately for me, I worked for many years exclusively on this, not knowing that I would be able to use it for other purposes. So it's been very useful. But it is very difficult. There are no general methods. You have to consider each class of matrix separately, study the structure, and then develop methods which are custom-made. So it depends a lot on experience for each kind of matrix functions. But once you have it all. Because we can, for instance, reduce the invertibility of this truncated Toeplitz operator to the invertibility of this, and this can be reduced to the existence of a factorization. And we have the expressions, the explicit expressions for the inverses in terms of the inverse of the Toeplitz operator. So the whole difficulty is here to get this. Now, how do we see that the operator is actually invertible? This is, of course, connected with the question of studying the kernels of these operators. And so we can ask a very natural question. If we have a truncated Toeplitz operator with a certain symbol, and an asymmetric truncated Toeplitz operator with the same symbol, they will have essentially the same properties, but now involving two model spaces. What is the relation between this kernel and that kernel? And the relation is, like in this picture, this kernel is contained in that kernel. So, if I want this kernel, I can think like this. That other kernel is bigger. So maybe it is easier to find because it's bigger. So if we can characterize this bigger kernel, then we just have to take the elements of the bigger kernel, add some extra condition to single out those ones. So we just have to take these elements and see whether they they satisfy this condition. And then we will have the kernel of this operator. So we are dividing the difficulty into two steps. For instance, suppose that the symbol is of this form, some G1 plus alpha, which is an inner function, times H plus, which I assume to be analytic and bounded in the upper half plane. And then this kernel, for the truncated Toeplitz operator, is contained in that bigger kernel, where I can choose my second model space, I choose it to be alpha. And since I have this alpha here, I can drop this term because this just corresponds to the 0 operator for this case. And so instead of this, I can consider just G1, which hopefully will be simpler because I could drop a part of the symbol. And if we see this in terms of Toeplitz operators with matrix symbols, this corresponds to solving two boundary value problems called Riemann-Hilbert problems, matrix Riemann-Hilbert problems. For this case, we have this matrix Riemann-Hilbert problem. We want this phi1 plus, which will give me the kernel. And here I have this matrix with this non-diagonal term. If I have this, then this corresponds to solving a Riemann-Hilbert problem of the same type, but in principle it will be simpler because I have everything equal except this non-diagonal element, which is simpler. And I can use this reasoning to study many classes of truncated Toeplitz operators. Namely, for instance, if we have what we call theta-separated symbols, we call them theta-separated because beta bar multiplied by theta will give alpha. And here H plus is analytic in the upper half plane, this is analytic in the lower half plane, so there are two terms. And we can think, as I said, we take this, we want to study this kernel. Okay, so we choose this bigger kernel to study, and we can drop this term. So just study this one, and this one has a symbol which is analytic in the lower half plane. We can study it. We see that the kernel is a model space, another model space, another inner function appears here, gamma, but it's not very interesting. So we can characterize this bigger kernel. We impose the extra condition, which now becomes very simple, and we can characterize completely the kernel of this truncated Toeplitz operator. And it turns out that it is a model space, which is here, gamma and gamma 1 are inner functions. So it is a model space that appears here, multiplied by some inner function. And if we do exactly the same to the adjoint, you see that it is exactly of the same type, the same model space multiplied by some function, which is an inner function. And therefore, I repeated the expressions here, we see that basically apart from this function, which is different, they depend on the same model space. So one is finite, this kernel is finite dimensional, like that one. If and only if this is a rational inner function, so a finite Blaschka product. It is injective if and only if this is 0, which happens only if this is constant. And if theta is a singular inner function, like an exponential, for instance, then the only possibility for this to be finite dimensional is for it to be 0. So we see that if theta is a singular inner function, like an exponential function, for instance, these operators have this very remarkable property, which is that the essential spectrum will always coincide with the spectrum because they are Fredholm if and only if they are invertible. In general, even if this is not a singular inner function, we see that they have the same dimension if they are finite dimensional, and either both are finite dimensional or not. And using results from Toeplitz operators with matrix symbols, we know that it is invertible if, this is not an if and only if, but almost. We have conditions for invertibility in rather simple terms involving the data of the problem. And in particular, for analytic symbols of the same type of that corresponding to the Volterra operator, this becomes even simpler, and we can describe completely the spectrum of the truncated Toeplitz operator in terms of what is called the spectrum of the inner function. The spectrum of the inner function is very simply basically all the points in the upper half plane or the real line where the inner function approaches 0. So if it has 1, 0, it is in the spectrum of the inner function. If it does not have 1, 0 like the exponential, but it approaches 0, for instance, at infinity, this is a point in the spectrum. So we can describe the spectrum in very simple terms as, for instance, if H plus is continuous, as in the case of the Volterra operator, then the spectrum of the truncated Toeplitz operator is just the image by the symbol of the spectrum of the inner function. And we can do the same for the essential spectrum, for the point spectrum. We can characterize the eigenspaces. It's not really difficult. And I will finish with just one example. What I have said before can be generalized. I just put the simplest setting. And in particular, we can add poles. We don't need to have analytic functions. Poles are not really a problem. We can always deal with them. And so we can consider a very simple case. Although very simple, it is very important. It's considered in any study of spectrum of truncated Toeplitz operators under the name of the restricted shift or the restricted backward shift. This has also been studied from the point of view of numerical ranges and numerical radii. And it's a case when the symbol is a rational function of this form with a quotient of two first-degree polynomials, because in this case we have a particularly simple and clear from a geometric point of view description of the of the spectrum. And we just take the curve defined by this, which is the range of this. So you can think of the unit circle, for instance, if we have x minus I over x plus I, and if we denote this curve by gamma r, the spectrum consists of the image by r of the spectrum of the inner function, and it is the union of two disjoint sets, the point spectrum and the essential spectrum. The point spectrum consists of the elements of this set which are on the contour, on the unit circle, for instance. And the point spectrum consists of the points of the set which are inside the unit circle. There is nothing else, and this is very clear from the geometric point of view. Of course, there are still many classes of truncated Toeplitz operators and many properties to study. This is clearly related also to advancing the study of Riemann-Hilbert problems and factorization problems involving triangular matrix symbols. But at least I hope to have shown that this is a promising method to study the spectrum of these operators. Thank you.
Okay. Any questions?
You mentioned for factorization conditions for the invertibility of Toeplitz operator. It seems they come from the famous paper by Hochberg and Krein.
Yes, in the beginning, yes, but they don't give, how can I say, there are no general conditions for knowing when the factorization exists. When the factorization exists, we know for significant classes of functions, namely all continuous functions, for instance. But in general, for matrix functions, we don't know when it is canonical.
Oh, sure.
But in this case, we are dealing with in the cases that interest me most, we are dealing with a very difficult kind of matrix symbols, which have exponentials in the diagonal elements. And these, in fact, we don't even have criteria to know if the factorization exists. So in the case where we have finite Blaschke products, this is clear, because the matrix symbol will be rational, and this is completely contained in what you can deduce from Gochberg and Krein's paper. But when you are in the infinite dimensional setting, which is the more interesting case, then you cannot, it's very difficult in general to know even if the factorization exists, because you have these oscillating elements in the diagonal which have no factorization in the sense of Gochberg and Krein.
Yeah, in general it's complicated. I just meant that you mentioned the book by Michlin, and
yes, yes.
The paper had to be mentioned too.
Of course they mention Gochberg and Krein. It's I like it very much. I know it by heart. So it would be difficult for me to mention all the authors. That's why I mentioned this book, which I like very much, and it has all this information.
Okay, thank you.
Any other questions? No? Okay. Oh, sorry. Right.
Just a small question to clarify something for myself. So in this factorization, the operators E and F, do they have to be bounded or can they be bounded?
Yes, this was on the upper part of the slide, which is I always take linear bounded operators. I only consider bounded operators, but the unbounded case is very interesting because I only considered bounded symbols, but I could consider L2 symbols. And in that case, we would have unbounded operators, which is something that I have not studied, but I think is very important. If I had unbounded symbols, and I would have densely defined operators, and if they are bounded, there must be some relation like this, but I don't know which it is. And then E and F would have to be unbounded. Exactly how, I don't know.
Thank you.
Any other questions? Okay, then let's thank the speaker again.